Let's try that again. Okay, and I should turn on my, okay, great. Today is a special day. It's a sad thing that today is the last day where I'll be able to give a fulsome lecture to you folks, at least this year, and I thought I'd use it to not so much just to further one particular topic or one particular sort of technical line of discussion, but to look more broadly at some of what I see as broad frontiers that are really promising within the simulation space, and to give some sense as to sort of the edge of the envelope, as it were, when it comes to modeling, some sense of where work is being done that I think is quite exciting, and hopefully some of the things that I talk about will cause you to reflect on what you've learned in the course of the class. We'll be reassembling several times for me to go over material in preparation for the final exam. So there'll be plenty of time to reflect explicitly on some of the details. And today I'm keeping my comments at a very high level. And as you know, I like getting my hands dirty, getting your AnyLogics fired up, and you're getting a chance to use Vensim to investigate things. And so it's difficult for me to avoid going into more detail on some of these things. Next year, I'm going to be rolling out an advanced version of this course. So there's going to be a basic and there's going to be an advanced one in fall and then spring semesters. And many of the topics that I'll be covering here will actually be featured in that advanced modeling course. Today, they're going to remain mere glimpses, phantasms, and be visiting us just in a cameo sort of way. And chances are I may not even get all the way through this because there's a lot of interesting stuff about these, and I may go on more than I should about some of them. And if that's the case, I may finish the lecture and post it in another video to complement what I do give here. Simulation modeling is a field that right now is rapidly advancing. It's of rather recent origin, particularly for some of the types of modeling we've been looking at, like agent. Oh, yes, Marina. Yes, I'm sorry, your arm must be getting sore.
When you're talking about the advanced course, is that like going to be like a 400 level course? Or
Yeah, 400 level. That's right.
It's going to be offered at the same term?
No, be offered. One will be. So I'll be offering this one, I think, next fall, and then that one next spring.
And we'll be able to take a 400 level course?
I'm sorry?
We'll be able to take a 400 level course then?
Yes. This will be the prereq for it. You'll be able to take that. Yep. I mean, all this has to still get into place, but I'm hoping to have a graduate version that would accompany this. So it would be a graduate advanced one and an undergrad, and they meet together. And that one would have a lot of project-based stuff in it. So it would involve. It would be less prescriptive and less driven by, problem sets and pop quizzes and pop quizzes and pop quizzes, and more chance to explore projects and to sort of pursue certain lines of interest more deeply, and potentially to partner up with people from diverse backgrounds to deliver insight. So the exact form of it still has to be worked out. It'll be the first time it's given, but it should be fun. I'll guarantee you that. At least fun for me. I think fun for you. Okay. Today's lecture, as I said, I'm going to be focusing on open frontiers in modeling. And I highlighted some modeling frontiers here. I sort of sat back and thought, what are some areas that I think there's lots of stuff going on that I wish I could convey to you in the course of this semester, but which there isn't time, but which really worthwhile stuff. And one of the issues is hybrid modeling, multi-scale modeling. And we're going to be spending some time just take a look at some of the sorts of hybrid models allowed. It's a particularly irony that I don't have a chance to give a full lecture on this as I was originally want, because AnyLogic is a wonderful tool for doing hybrid modeling. That's where perhaps its greatest relative strength lies, is the capacity to mix together these sorts of models. Not only use the same package for different modeling projects using each of these models, but within the same model have system dynamics, have agent-based, have discrete event modeling playing out. And we'll take a look briefly at some ways of doing this, but more to the point, I put on the website, on the Moodle site, something like 5 or 6 hybrid models, which show different configurations of hybrid. They show things like agents who have stocks and flows in them and whose dynamics are described by stocks and flows. It shows situations where you have agents who can go into a discrete event model and come out of a discrete event model, so to speak. And we have situations where agents can, I don't know that these are illustrated in those models, but I'll talk about it, where agents can contribute to driving a system dynamics model. So this first one, I'm talking about it. It's because I have a conviction, and it's based on a lot of experience with these different sorts of models, that they're highly complementary. You'll find people out there who are this or very partisan for one sort of modeling, and they'll get up there and they'll say that this is the type of modeling you should be doing, and the other types are subservient to it, are obsolete, or are not nearly as useful. And I have to take issue with that. I think there's really substantive reasons for using each of these types of modeling we've seen in the course. And the reasons cross from issues having to do with what you can demonstrate formally or mathematically, to issues of convenience, to issues of skill sets that are available, to issues of ease of representation, to issues that certain types of processes, certain types of information about processes are much easier to collect in certain models than others. And my experience suggests that multiple modeling types are highly complementary. And what that means is in a given line of investigation, a given research direction, or a given problem, you may use several types of models, but you may also want to use them together. So no one system science methodology offers a replacement for the others, and significant synergies can be secured by using combinations. You really, I introduced the course by talking about system science or complex systems methods as the science of the whole. It's about understanding the whole as greater than the sum of its parts. And so it is with these methods. I think when you combine them, you can get insights from that combination that transcend what you can get through each method in isolation, or even by the sum of these methods. Here we have a situation where there's lots of opportunity for securing deep insights from selective combinations of them. And as we'll see, it reflects the fact that there are competitive advantages. It's not merely one's interchangeable with the others, and it's not merely that one replaces all the others. It's that they each have strengths, they each have areas where they shine, and by combining them creatively, that's where we can really secure the greatest mileage from them. So we found use of multiple frameworks in our work to be highly effective. That may involve co-evolving multiple models aside each other within a single model. And within a single model, I'll throw examples of things. Some of these are illustrated by actual models that are in Moodle right now. Others are in the hybrid modeling section, hybrid example models. Others are ones which we've worked with or we're working on right now. And if anyone's interested, I could share. But here's an example where you might want to model a population, most of a population in stock and flow sort of way. Maybe you don't need to accumulate great detail or great information longitudinally on someone's history or biography, as it were, for most of the population. But at some point, those people may get individuated into agents. They become agents. They flow down here, and suddenly they become an agent. And as an agent, that may afford you a greater detail of understanding, for example, how that particular agent is evolving over time, their encounters, their particular history, their particular biography, their particular network location, their particular location in space, their unique characteristics. So here you can secure great computational economies by running upstream factors like this, where you don't need the detail, and then you get the detail where you need it downstream. Fairly easy to do in any logic. As they come out of that flow, you create them as agents. They're budded off into agents. Okay. Another situation you can get is, it may be that there are certain types of factors that you want to capture within your model in a more detailed sort of way, and that end up driving the activity or the action in a system dynamics model. So you may have agents circulating, for example, in detail, and they drive a flow which is in a stock and flow model. And the stock and flow model has other flows in it, and captures some high-level information, for example. So maybe interaction between companies leads to more product being sold to consumers, for example. Certain consumers adopting a product. Or it may be that these agents are agents involving something about the context of these people in the population. So we can have agent-based models driving system dynamics models. And often we'll see in any logic, you might have a system dynamics model that describes the environment, the overall sort of context of the environment and its dynamics, and then we have agents who circulate within that environment. The more aggregate character of the environment is captured. And another type of model which you'll find in your Moodle, in some varieties, there are agents, each of whom has stocks and flows evolving within them. So these stocks and flows might involve something like blood sugar levels in a diabetic, or they might involve levels associated with, there might be a stock associated with their weight, and the weight changes over time in response to, their diet and their physical activity level, which might be influenced by other people in their social network. And so here we might capture the evolution of an individual, certain aspects of them in a continuous fashion, and yet they're embedded in an agent. That agent might also have state charts, or they might have variables of other sorts, but certain aspects of their state, of their current status, would evolve in a continuous fashion using stocks and flows. So there's a number of models on Moodle which illustrate that. Some built in more detail than others. Another model you'll find in Moodle, which is a model where we have a space tessellated, gridded up into squares, and each of those squares has a dynamics characterized by stocks and flows. I believe I could run this for you. It actually can elicit some fairly interesting behavior. Well, many of these I could run for you, but I don't have time. This one is particularly interesting. So let me see. Here we go. This again is on Moodle if you want to frob it some. Here we have these individual patches, and the patches have internal dynamics characterized by stocks and flows, and the patches speak to each other. So here we have there's connections between patches, for example, net migration to nearby patches from other patches. So there's sort of a diffusion process going on. And over time, as this model runs, you have cells talking to neighbors. This is in a toroidal topology. What do I mean by that? Can anyone say? Those who go to Tim Hortons may be particularly familiar with toroidal topologies. Yes?
So it's basically a donut.
It's a donut.
On all the sides.
That's exactly right. So the left is connected to the right and the bottom to the top. It sort of wraps around in these two ways. You can imagine sort of wrapping it around and around this way, and you will get a donut out of it. Now, unfortunately, as it's displaying it with screen capturing and so on, it's not quite as evocative as it is when you run it full speed here. But you'll start to see certain emergent patterns coming out of it, having to do with sort of network diffusion across the screen. You'll see these kind of expanding wave fronts, etc. Fundamental sort of PDE here, for those familiar with it, partial differential equation. You could capture the wave equation or the heat equation, what have you, in that sort of context. So that's fairly simple to do in any logic. Another example that's on the website is a hybrid agent-based and discrete event model where you have these agents circulating the population where they come in, they present for care within a long-term care facility here. And they are attended to by various doctors, various clinicians, some of whom are clinicians in training and some of whom are very experienced clinicians required for certain tasks. So they come in, they present for care, and at some point they're delivered care and they can then go back into this population. There's a particularly simple one that's used as an alternative to this on the site that should let you understand how that happens. Again, this is very straightforward to do within any logic. You can so-called inject these agents into this as entities into this discrete event simulation, have them circulate there. When the entities disappear, the agents are still around. And for those from computer science background, the way this is accomplished in detail in this version of AnyLogic 6.9 is through subclassing. It's even simpler in AnyLogic 7 where the two are the same. Entities are agents. So with hybrid modeling and multi-scale modeling, we have lots of opportunities for embedding submodels within a broader model and capturing, therefore, dynamics of various sorts within a sort of a hierarchy of models, as it were. Lots of opportunities there. People are grappling with what the trade-offs are between these types of models and how to use them most effectively. And it seems that multi-scale and hybrid modeling do bring some extra insights to the table in certain cases because they allow you to use just the pieces that you need to describe a situation the way you want. It doesn't force you into just one way of describing it. You can kind of mix and match your Lego blocks, as it were, to build it up. Next, I don't know how much the undergrads here are aware of it, but there's a sense right now among those pursuing scientific research that we're entering an age marked by markedly increased levels of access to empirical data. In other words, data about the world. These data are, in the health area, streaming in from all sorts of different sources, and people are just running to try to make sense of the data sources opening up. These include sources from social media, places like Twitter and Facebook, etc. It includes environmental sensors, which are increasingly implanted. It includes biomedical sensors, which people may carry around. And there's a lot of heady talk, some of which I think is hyped and overblown, that labels it with this term big data. The term big data is also, I think, a poor way of describing it. But the idea is we're dealing with just massive quantities of data. Of course, short of an ability to make sense of that data, that's just collections of numbers. full of sound and fury, signifying nothing. So, we're building here a variety of simulation models aimed at informing decision making in a variety of areas, particularly in health. And we find that these models have a real need sometimes for data. You think about a model at the agent-based level. We talked early on in this class about models as dynamic hypotheses, so capturing some sense of how the world works. And it turns out if you really drill down into it, there's a lot of areas of human behavior where we really don't know very well how the world works. We know certain things in it from past studies that have been done, but we don't know sort of moment by moment or minute to minute exactly how things are playing out. We have some guesses. We have in some cases, pretty good guesses. But traditional instruments like surveys, questionnaires you fill out are just not very amenable to asking about your contact patterns as they vary every 5 minutes. It's hard enough for people to remember who are the people I spent with, most of my time with in the past week. And if you have to report those things, within an hour's time with surveys, you'd say, forget about it. This is way too much burden. Yes, Sarah.
Another point with surveys is that people will often have interviewer bias, so they'll provide responses that they think make them look like a good person to the interviewer, even though this person doesn't really know who they are and never seen them again. It's just this natural tendency to make ourselves look better. So if you're asking about something like dietary habits, somebody might downplay how often they eat fast food or be more likely to report healthy eating behaviors.
Right.
There's just no way around it, really.
Yeah, it's a good point. We've done some studies here on campus, quite a lot, in fact, with smartphones, and compared the data on where people actually go. This is all going through consent, and we do these studies. We've been very proactive with the ethics office. You compare what they say to what actually is being done. It's a world apart. Where do people say they spend the most time? The gym, the classroom, and the library. Where do they actually spend the time? No, none of those three. Spend a lot of time in Place Real, particularly in the bus area sometimes. But yeah, there's often distant relationships. So when it comes to reporting location, or reporting level of physical activity, or spatial proximity to other people, or diet, or social context, or communication, often people are going to have very poor and selective memories, and sometimes very poor reporting accuracy in these areas. And the problem is that these behaviors are quite important, and we have models which can try to represent them, try to posit processes at that level, but if we can't ground these models with real understanding, we may be spinning our wheels, we may be speculating in ways that is not going to be very helpful. So, just to give you one example of sort of the big data thing, one thing that we've been taking advantage of is indeed smartphones and increasingly wearables too, things like smartwatches, etc. And the observation here that many of you are familiar with are smartphones are amazing devices. They've transformed many day-to-day sort of activities that people engage in, transform what it means to go ride the subway in Toronto or what have you every morning. But many of these changes, many of the functionality we find so appealing about smartphones is functionality enabled by sensors at some level. And I'm speaking sensors broadly, including things that can sense a Wi-Fi network and therefore, detect a Wi-Fi point where I might be able to send a queued out email, or GPS sensors, cameras, microphones, the very types of devices you might be recording me right now. And the point here is that such sensors can be repurposed at little or no cost to their original function. And we're surrounded by these signals all around us that give us context, that tell us something about where we are. The fact that we see certain Wi-Fi points more strongly than others tells us we're probably in some corner of the world. There's GPS signals, there's Bluetooth signals that can be used to measure location in greater detail. So we've been using IEPI, this app that we've created for a number of years and is being used by a variety of international partners for informing understanding of health. And it can fill in a lot of details in exactly these areas: physical activity, people's location, their proximity to each other, aspects of their social context, communication, etc. Now, my point here in citing these things is that this is one example of the sort of areas that are opening up for data collection. And there's a synergy here between these two, because the more data you get from these sort of mechanisms, the more models are needed to make sense of it. After all, the models are what, we've seen it through the term, can often link up some understanding of the situation to the choices and allow us to evaluate the consequences of different choices. How much does reducing contact patterns help? How much would it help in Saskatoon to blunt a bad influenza pandemic if we were to shut down schools for several days, for example? In order to understand that, we need models to kind of put together those pieces, put together the pieces of contact and risk from transmission of a given contact and how long people stay infected and all those sorts of things. So these models help us. Oh, is this? I'm just making sure a remote person can still see my screen here. So the models work in conjunction with big data, but at the same time, the big data grounds the models. This data that we can collect can help inform the models. Can help fill the gaps between can help ground the models in observations, provide databases for model parameterization and calibration. It can stimulate ideas that would be represented within the models. Okay, great. We've explored a variety of ways of interfacing these sort of models with these sort of data collection. And they include parameterizing models to data. So we have models, any logic models, where the connections between agents are exactly the connections that were reported for real people in our area of the university, for example. So during the flu pandemic of 2009, 2010, we had people carrying devices, recorded contacts on the granularity for about a minute in length. And you can feed those into models to actually drive the network, the connection network, a dynamic connection network within the models. Another thing we can do is drive mobility patterns in the models. We can have the models sort of replicate what was going on in the world. But that's just one way of many. We can calibrate models to data, so see if the models reproduce certain patterns of data. We can also do some sort of inferencing based on the models in a way that will allow us to estimate certain aspects of state charts that would then go into the dynamic model. We can train the models on the data. For example, we might have models and this is actually a separate issue. We might have statistical tools that try to recognize certain patterns in the world, and we actually use an agent-based model, for example, as a synthetic source of data to see how well the statistical model, a hidden Markov model, a machine learning model, classifies things before we use it on real-world data, or to do it so that we know what the underlying ground truth is. We know what the underlying situation is, and we can evaluate this statistical model, how well it classifies things. So here the simulation model is being used to kind of test and to evaluate and to refine statistical models, and machine learning models. Models that make inferences about things, that classify when someone's indoors or outdoors, when they have the phone on or not, or when they're in proximity to another person or not. So we've been combining sort of data from phones or from other types of data sources like social media and browsing behavior, etc., together with these sort of models in a variety of areas. And I've mentioned some mobility models and H1N1 transmission models of flu, models of people's smoking behavior, which again, it involves dynamics which aren't very well known minute to minute, but which we can pick a lot of information up on phones. So So this area of kind of big data, or what's sometimes called data science, kind of making sense of this growing ocean of data. Data that's marked by four things, the four V's. Volume, huge amounts of volume. Velocity, it's coming in real fast. I think with our phones, we get something like 1 million records per person per month, something like that, streamed off the phone. So volume, velocity, veracity. So it's less subject to reporter bias, less subject to recall bias, etc. So less subject to sort of confabulation. There's another fourth V, which I'm forgetting right now. But velocity, veracity, volume, and fourth one, which I'll tell you at some future point. So here we're increasingly seeing data marked by those four V's, and increasingly it's in the context of models of some sort to make sense of it. And the sort of dynamic models we've seen in the context of this class are great examples of models that will be absolutely key in turning this sort of data into information, into knowledge, into value for decision making, for making choices. Another topic that I want to talk about is linking up simulation models with computational statistical tools, and particularly for doing real-time predictive simulation. This is related in the sense that it's making use of data, but here the focus is kind of on some of the statistical mechanisms and the way they interact with the simulation model. So the idea here is, ladies and gentlemen, is motivated in large part from the fact that with these sort of models we've been building this semester, even the most grounded model, the most detailed model, the model we spent a huge amount of time building up and refining and crafting, that left to its own devices, set off on its own, and run forward, it will inevitably diverge from the real world and what's happening. Models, I argued early on in this class, are like maps. And their power comes from the fact that they abstract away from certain details, they leave out certain things, and inevitably they will be leaving out some processes that are factored in the world. And there's factors that are essentially stochastic, which we're never going to be, at least anytime that soon, we're never going to be able to predict with enormous confidence, that are going to make a difference to our model. And so a model's going to diverge. Even if it's a very good model, it's going to have some divergence from the world, left to its own devices. So the idea here is to create closed loop models that are constantly kept honest, constantly regrounded in actual observation. So instead of being a matter of you build a model and then you use it, you build a model and then you try to derive insight from it. Once it's built, it's kind of fixed. Instead, to turn to a situation where the models are constantly being updated by new knowledge, new information, constantly being tied to the latest observations so that they're most fresh in their current estimates of what lies forward. This offers particularly value because there's a prospect here that very rough and ready models, built quickly, slapped together early on before all the details of a situation are known, may still offer a huge amount of value in projecting forward if they can just be regrounded consistently. If you can just bring them in line with what's actually observed, they may serve very useful vehicles for sort of projecting forward. If they can learn from new data as it comes in, as it were, and get constantly refined and crafted, it means that we don't have to spend months and months and months building up this model only to find now the situation is past. We instead can, while the iron's hot, act by using a model that's going to be undergoing a learning process. So left to themselves, data incoming data is just not going to offer a lot of value. It doesn't let you project forward, doesn't let you understand the consequences of different interventions. Data points by yourself about what's been seen are often noisy, they're error prone, they don't let you look forward. It's like looking out your back window while trying to drive, and they don't let you understand the trade-off between your choices. Models, on the other hand, have a great deal to recommend them in those areas, but they can get inaccurate. They can get highly inaccurate, and particularly as you run them forward over time. So the goal here is to try to combine the best aspects of these. And I may have shown you this slide before. I can't remember. This is a graph from a Predictor-Corrector model, and it's got some imperfections in it. This is an earlier version we were working with. In this particular one, it's a particle filter. The idea here is that we have a model building, that's projecting forward a wide variety of outcomes. The model itself is stochastic, so it's not sure which way things are going to go. And then new data comes in, and that model is regrounded in this data. It says, okay, so here was a data point. It hit it, so here it wasn't sure the way things would go. Okay, so it's still low. It's guessing it's low. Okay. Oh, here's a data point. Okay, I'm going to think, this is probably what's going to be going forward. Here's a new data point. Oh, forget about these things. It's all about this area. Here's another data point. It sort of bumps it up to there. Another data point bumps it up to here. And it's constantly being regrounded. This model that I'm running this on here is far, far off from the underlying ground truth. I know, because I'm feeding it with data generated from an agent-based model, a model which I know exactly what's in it. And the actual model that's being corrected is far off. It's got big distortions, big inaccuracies. It's aggregating a lot of things. It's not representing the network. But constantly regrounded, it offers some predictive ability. And it turns out you can do often quite a bit better than this. You can get a model that's quite accurate going forward for short periods of time. And the beauty about it is you can deal with the noisy data and deal with the fallible model at the same time by getting them to complement each other, by getting them to compensate for their own weaknesses. The model knows the noise you see in this data, a lot of it is probably just measurement error or distortions and trying to estimate things when we measure them. And at the same time, the data can deal with systematic inaccuracies in the model. There's many ways of doing this. One of them is particle filter we're using a lot, and we have particle filters implemented in AnyLogic that work very nicely with models and that prove very useful. Another example that's much older that some of you from engineering may be familiar with is something called the Kalman filter. And the Kalman filter is something that was first defined in the 1950s, and it again involves blending measurements over time with model estimates to come up with a kind of consensus estimate, taking into account the fact that sometimes one is more accurate than the other, and that may change over the course of the simulation. So we have Kalman filter going on, and an estimation process, and new measurements coming in, and this Kalman filter is projecting forward. Kalman filters are used very widely in systems like planes and missiles and rockets and those sort of things. But here we can use them in a wide variety of areas. The particle filter is, in some sense, a generalization of Kalman filter ideas. It can handle a broader set of cases and takes advantage of the fact that often there's much more time between measurements in certain domains, such as health or business. So I've noted some ways of sort of keeping these models updated. There's another line of work that goes on. We talked in this class about calibration, and calibration being this process of estimating parameter values. And often what you get out of calibration is a point estimate of parameter values. These are the most likely parameter values, or these are the best fitting parameter values. Sometimes you get out estimates of confidence intervals around this that recognize sort of, well, there's some uncertainty. Maybe more uncertain sometimes and more certain at other times. The problem is that this has a number of limitations to it. It's assuming a single dynamic model. It's assuming your model is correct. It's just your parameters which are wrong. If these single point estimates don't make clear, for example, how, if you have a single point estimate for a parameter, it's not clear that that's going to give you the best point estimate for outcomes of the model. Maybe it's a best estimate for that parameter value, but if the model's nonlinear, the best estimate for the outcome may be different from what you get by running the model, this nonlinear model, and the best estimate for the parameter. Even if you have sort of confidence intervals, you're often assuming it's unimodal, that you kind of, it's right around some peak, some single peak. And there's some technical assumptions that go on with this. So what a growing number of people, including ourselves, are applying here is putting aside just a classic calibration context and instead trying to arrive at a distribution of possible parameter values. So the idea here is that we try to arrive at what's called a posterior distribution. We start with some best guess as to what a distribution might be for these parameters, but that guess is often just totally overwhelmed by the data available. And then through a certain process known as Markov-Chain Monte Carlo estimation, we can arrive at a distribution estimate for the parameters. So instead of getting just a number out, the number of contacts per unit time is the best estimate is 7.53. Instead, we get out a distribution of that. We get out a distribution. Well, it may be centered at 7.53 in some cases, sometimes maybe not. But, one standard deviation out, it may be, 8.2, and then it may stretch out further. But in general, it might not be a normal distribution. It might be any number of shapes. So the idea here is that we try to arrive at a distribution over these things. So we can arrive at, for example, here is a joint distribution over two parameters. So this parameter could be larger or smaller. This parameter could be larger or smaller. And if this one on the x-axis is larger, it means the other one must be larger too. So there's a joint distribution. You could say, well, you could have high for both up here, or you could have a low value for both. But it's unlikely this one will be very high and this one will be, for example, very low. They sort of go together. And sometimes you can get the opposite. Well, you can assume a high rate of contact and a low chance of transmission, or vice versa. Okay, so those are some computational statistical tools. These are tools that are taught over in math and stats, and we work with colleagues in that area for that reason. But they are of great value as simulation models. And simulation models can be greatly leveraged if we can make use of these tools. And these tools, in turn, help us make sense of this cacophony of big data. Okay, another thing I'd like to talk about is this issue of agent languages. I actually was going to put something in here on some aspects of model software engineering, extending testing techniques and mocking techniques and use of interface-based programming to models, things that Dustin has heard me utter about in the past. So the use of mocking to kind of allow you to, for example, here, test a model, not all at once, everything together, but to test person without needing to go test main, or to test main just assuming very simple things about person. You mock it out for now. It's kind of a stubbed version of it. Maybe it checks some basic things when you call it are true, but it allows you to focus on testing just pieces. And in general, the issue of testing models effectively, using them together with assertions, which are techniques we use in software engineering. This is largely open ground. Very few people have explored it, and I'm happy to say that we're doing some of the leading work in this area. Priessery here is doing work in combining aspect-oriented programming with models and has been using it as part of that project to make some observations on their models. So there's a huge amount of opportunities for combining software engineering techniques with models in a rigorous way. So I had a meeting at 3 o'clock to 4 o'clock today. It was about a project that we're involved with, which involves a model. It's not in AnyLogic. It's in another very competitive framework for AHU-based model called Repast. Maybe the #1 framework out there. And this model involves 216 Java classes that you have to manage. About 25,000 lines of code. And it has 750 what I call magic numbers or manifest constants in it. Anyone know what that is? A magic number in a software program? Sorry? Sorry, I didn't catch it. Yeah, well, it actually is not, it may be grounded, so I'm not using it in that sense, although I could understand why it would be used in that sense, but it's used how? It just appears in the middle of the code. 3.2. Where's that from? What does that assume? Is 3.2 really the ratio of, maybe 6.4 divided by 2.0? You don't know. So if you want to make a change in assumption about the model, how are you going to find all the constants it depends on? Suppose that 6.4 divided by 2.0, maybe that 6.4 means something. It's the odds ratio for a smoker, encountering cancer in their 20s or something like that. And now we want to change that because the new evidence has come out. It's actually 6.6. We want to go search in our model. We could search for 6.4. We won't find 3.2 because even though logically it's dependent on it. And it's a big mess. We don't know this 2.0 in the model. Where is that from? Is it the 2.0 associated with this or associated with that? Is it logically, if we change one, do we have to change this other one? It's a big mess. 750 of those in this code base. Issue after issue that comes up. Software engineering is often a skill that's underplayed by modelers. And if you can undertake both modeling and software engineering, your skills will be greatly valued. Very few people can combine those tools. And there's great opportunities for doing some basic things that we assume in professional software engineering, like mocking, like using assertions, like continuous integration, like using languages specific to use, like handling dependencies, using tools like ANT or make, etc. These things, for a lot of modelers, they're not aware of them. Another thing, though, I want to talk about is the language side. Some of you may have noted, particularly those not from computer science background, you probably found encountering system dynamics models in Vensim easier in some sense, more accessible than the models in AnyLogic. And the reason is, in system dynamics, for years now, for decades, there's been a focus on what I call declarative model specification. You describe the what of the model you want to build, and you let the system figure out the how. You describe, okay, there's stocks and there's flows, and they're linked together with this, and flow depends on a stock in this sort of way, and the model figures out all the details of how. You don't get involved in variable declarations and for loops. You don't get involved with the software engineering of it. You sort of characterize what you want to be simulated, and a modeling framework will take care of the details. Now, in AnyLogic, you're using a general purpose programming language, and that does afford us a certain flexibility. But the fact is that often modeling projects get terribly bogged down in software engineering, like the one I mentioned. And they can become immobilized because you're unable to make progress because there's bugs in there and you don't know how to change the assumptions effectively, etc. And the issue here, folks, is a lot of this is an issue of language. It's an issue of the languages we're using. And we're using languages, frankly, for agent-based modeling that are not very well suited to it. AnyLogic does a pretty nice job giving us state charts, giving us events, and making use of action charts even to illustrate algorithms. But you still end up doing a lot more in Java than you would do in Vensim. And we're working with declarative specification for agent-based models that might make creating an agent-based model as transparent and as declarative as creating a stock and flow model in Vensim. So that, again, you specify the what, and it takes care of the how. And we've actually made quite a bit of progress. I don't have the opportunity to show this here. How many people in here have taken 340? I would urge you to think about it. It's programming languages. And you will have a glimpse of programming languages that are probably very different than what you've encountered before. Programming languages that are declarative in character, like Prolog, and programming languages that are functional in character, and that have elements of declarative, like Haskell. It really exposes you to new ways of sort of thinking about programming that are going to be increasingly important for professional software engineers. These sort of things are becoming quite prominent now with Java 8 bringing in Lambda functions and functional programming style for JavaScript, etc. Languages like Scala coming to the fore. So if you have a chance and you're around for another year, I'd suggest you think about taking 340. Now, we can adapt some of those ideas that come up in the course, as well as many extensions to those ideas, to agent-based modeling. And actually, I'm working with Professor Duchin on exactly that issue. Let's talk about this issue of evaluating synthetic populations. So one thing we haven't talked about is these agent-based simulation models, for example, we can use them to evaluate inferences that we might make on real-world populations by doing it on the simulation. The advantage is in the simulation, we know the exact situation. We know what's going on behind the scenes. We know the so-called ground truth. And so if our inferencing scheme, our scheme for sort of deducing something from a bunch of data from the real world, if it doesn't hold up when it's given the synthetic data, if we see a real disparity between what we know is going on in that underlying agent-based model, for example, because we programmed it, we told it what to do. If we see a disparity between that and what we're inferring from that data, it's kind of dicey to think about taking those techniques to the real world, where we often don't have the luxury of really knowing what's going on beneath the surface, where we're dealing just with this data to make sense of it, and we don't know if our conclusions are accurate. So we can use these sort of models that we've seen this semester as fearsomely effective tools for evaluating, for scrutinizing, and for refining techniques that are used by, applied by statisticians, or applied in health theory by epidemiologists, or techniques used by marketers to infer something about, through conjoint analysis, something about people's demands, etc. There's a set of analytic approaches, possible study designs that can be very costly to implement in the real world. Think about a campaign to promote vaccination, or a campaign to go and try to estimate the prevalence of undiagnosed of TST positivity, MAM2 positivity in the community. These things are very costly. If we could try it out in our models first and see how well it does, when we know the underlying true situation, we can get a lot greater confidence that when we do go into the world, we'll be in a good situation, we'll be robust. So the idea here is we establish a synthetic population for sort of a virtual study in the simulation. And we simulate out the study within the course of the simulation. We may blind ourselves as researchers from the underlying situation. Someone else creates the model. We apply these tools and we see how well the study design performs, or how well our inferences from the underlying population. And we've done this in a variety of tools, including using data collected from the real world using sensors, and used it to evaluate a bunch of approaches. Another issue, and time is growing short here, so this will be one of the final ones with which I leave you, is this whole issue of representing agent decision making. The agents within our models, ladies and gentlemen, and to some degree when we've had to represent things in aggregate terms that we've used in these models, for reasons of pedagogy, they've been incredibly simplistic. I mean, we've had agents sort of bopping around in space, you know, in random walks. We've had them sending, you know, just being in networks and sending messages to a randomly chosen connection. They've been automatons. They've been stripped of their detailed agency, stripped of their preferences, and they've just been impoverished into probabilities. And we can do better, ladies and gentlemen. We can do better. There's whole edifices of social science which are built around the idea of studying human behavior. And there are tools that are highly well suited to merging with agent-based models to represent choices, people's choices over time. Whether those choices be, as somewhat often but classically assumed by economists, more rational, that people are trying to maximize some utility, some satisfaction in their choices, or whether they're more heuristic, whether they make use of rough and ready, quick heuristics to just allow them to, you know, get on with things. They'll make a quick choice between a bunch of different options, often based on very sketchy criteria, but it's good enough. It satisfies us. So it turns out that there's theories that have formalized study of how people make choices, and random utility theory and discrete choice theory bring to the table formalisms and ways of trying to measure these things, trying to estimate these things that we can combine with agent-based models. So, for example, discrete choice theory provides some grounded understanding of how people choose, whether it's through heuristics in some sort of rational, boundedly rational way. And some of the choice theories actually represent several stages of decision-making. They provide statistical tools for estimating preferences, for estimating based on people's survey responses, based on observed behavior, so-called revealed behavior on part of individuals, recognizing their likely underlying preferences, seeing them go through buying the same things day in and day out, seeing how they respond in the context of different choice environments. You might be able to deduce something about what things they prefer, based on their response to artfully chosen survey questions and questionnaires. You might be able to infer something about their strengths of preferences. So there are these sophisticated state of preference, for example, mechanisms that allow you with a minimum number of survey questions and a smaller number of respondents to elicit quite a good understanding of kind of people's attitudes within certain assumptions. So discrete choice theory brings that. Now, agent-based models can complement this by capturing changing choice sets, the fact that all through the day we're surrounded by different choices. Someone is in a lower income community where sidewalks are falling apart, where there's no opportunities for using parks, where or communities, gated communities, where the streets are all curved in a way that inhibits walking. They have very different choice sets than those who might be downtown with wide avenues for walking along the river, etc. And all through our day, we may be encountering different choice sets. In the context of our day-to-day experience, day-to-day dynamics, our location, our social context, our economic context, our choice sets may be changing. We can capture those dynamics over time in dynamic models, such as agent-based models. Agent-based models can capture experiences that change agent confidence about evaluations or preferences. Think about someone, so I have a colleague at Michigan, Liz Brewer, and she studies, among other things, people's mate selection behavior. And one of the things she spends time thinking about as part of this is, people's use of different ways of trying to find a mate in life. So, to what degree, yes? Oh, okay. That gave me a real fright. Okay, thank you. Wow.
Your network dropped.
Evidently, that's what I'm thinking. Oh my gosh, but it's plugged in. No. Okay, no, bad things happen. No, that's okay. Good things happen in the sense that a student pointed it out before it got too bad. We lost everyone, alas. Okay, well, okay, I'll right along. So these, within agent-based models, we can further. So this colleague of mine, she studies matrix, and one of the things she studies is what people use dating websites, or database. I understand there's a site called POF, and to what degree do people go to POF to try to find a mate? And the fact is that sort of behavior may come in the course of experiences someone has positive or negative experiences associated with POF or other sites, choose them to behave differently. So preferences evolve as well. People's conviction as to confidence about the choices. So when they choose between them, they think they know they're getting better. And the preferences evolve. And furthermore, we can capture influences of different people, preferences, or real-world responses to choices. So maybe I want the same thing you do, but only one of us can get it, and you do, and so therefore it's not available to me. So random utility theory posits some ways of representing choices I don't have time to go into, but one of the key things is it provides a mechanism, not only a sort of theoretic set of formalisms for estimating individual choice behavior, the probability of making a choice A, but it furthermore allows you to estimate. It provides very intricately crafted tools for estimating the parameters in these equations, so you can plug them in to your agent-based model. A final thing which I'll just close on is the issue of performance. I have a whole lecture on performance I could have given. It has very detailed suggestions how you could speed up your models, allow your model to go to eliminate performance bottlenecks. In ways you can use tools like profilers that we use in software engineering to figure out where the model is spending its time. There's a whole set of additional opportunities associated with concurrency. Some operations in these models are what we call embarrassingly parallel. So for example, if you're going to perform a sensitivity analysis, see how the model responds to different assumptions about parameters, you could farm those out to different machines, different computers, different cores on a given computer just fine. They don't need to talk to each other. Each of them is a solitude. Similarly, so it is if you're running the model again and again and again, capturing the response to different stochastics for just running to examine with different realizations. Sometimes, however, we can also capture concurrency within a network. Imagine taking a network that's divided largely into two communities and putting those on different cores. And then each of those cores can compute just those agents, and then they occasionally have to send message back and forth to each other to communicate. And it turns out the language impacts, when I earlier talked about those novel languages, one of their key advantages is we can get these running on things like the cell processor, which are using CUDA, so you can get it to run in parallel in a massively speeded up sort of way. So any logic essentially could run 100 times as fast by mapping it appropriately. And finally, I don't have time to talk about a variety of other frameworks that are out there. NetLogo, for example, is a popular one, Repass Symphony, and ModGen, which is a popular tool in governmental circles within Canada. Ladies and gentlemen, it's my great regret that I stand here today on the end of my last lecture in this course. It's been my privilege and my pleasure and my honor to be able to teach you folks. I know this is the first time we've had this course jointly in this sort of way. We just are getting things refined, I think, and I know that there's some hiccups and some things we still got to get back to you soon in terms of problem sets. I appreciate your patience in bearing with this. I've really enjoyed teaching you this term, and it is with no small measure of regret that that we're not going to be able to continue meeting. It is my plan to have two further meetings for the sake of preparation for the final exam, for me to answer whatever questions you have. And of course, I'm absolutely delighted if students ever want to drop by or make appointments to talk about any material. I often get questions from students, you know, do you remember me? I was in your class 3 years ago. Man, do I? Of course I remember you. Yeah. Come on in. You know, I'm happy to talk. I will tell you this as well. If anyone, you know, has an interest in pursuing any of this material, we do have partners from around the country, around North America, and on occasion from around the world, who are very keenly interested in partnering with student teams, who are interested in possibly hiring students, and we have projects that need work. The type of skills that you've developed in this course are not common to find. They're not common in the workplace. You have a very strong set of skills that you could bring to bear on some very pressing problems, and they are in demand. So if any of you are interested in pursuing this as a possible avenue, I could give you recommendations of where to look. We are lucky here on campus because every year we have one or more events that bring people internationally to Saskatoon, to U of S, to learn about these methods, and they're often looking for partners. So if you're interested, you know, trying a partnership with people on could get you some papers, could get you some money or what have you. We've had students hired at these events for consulting gigs, etc. So if any of you are interested in that sort of thing, do let me know. We're going to be having one very likely in late June and then another in August. And again, people come from Europe, from North America, South America, Asia, etc., Australia. So I'd be glad to clue people in if there was interest. Yeah.
Does this conference have a name that we can?
Yeah, it's agent-based modeling boot camp and incubator for health researchers. You can go find it online. And of course, it would be my great pleasure to spare all of you folks the costs associated with that. But other people do pay money for it from outside the university, but my students, it's a priority. And you folks could essentially help out with giving people advice. It's a lot of fun, and you get free food as well. So anyway, yes, okay. Very good. So again, thank you so much. It's really been a great pleasure. I'm happy to meet with students who have any remaining questions, advice on problem sets, you know, project advice. But thank you so much, and I'm looking forward to future interactions. And I'll try to let you know about that course for next year when we get that rolled out, in case any of you are still around. Okay? Thanks very much.